Okay, so good morning, everyone. We are in chapter 4. We have seen what we mean by errors, uh, and we have seen definitions for error, like the true error, the absolute error, and the relative errors. Then we have seen what we mean by approximate errors, and we have also seen why we have round of errors. We'll continue now to the next type of errors, which are the truncation errors. Truncation errors occur when we use an approximation instead of an actual exact mathematical procedure. One example is when we use the finite difference equation to approximate a derivative. So we have taken this in chapter 1 as well. We said we can approximate dv over dt to be approximately delta v over delta t. So we are just approximating the derivative to be equal to delta v over delta t, and we know, of course, that this is an approximation. The actual definition of the dv over dt is delta v over delta t with the limit of delta t approaching 0. But if you don't have delta t to be 0 and you take some finite difference, it means there is some value to it, it's 1.1, there is some value to it, it's not 0, then of course you are going to end up with error. So this approximation leads to what we call truncation errors. Another example is the Taylor series, and the Taylor theorem states that any smooth function can be approximated as a polynomial, and the Taylor series gives us a mathematical expression to express the function, any function, in the form of a polynomial. And we have taken this before in other courses. We know the Taylor series. If we have a point xi, then the function can be defined at point xi plus 1 using this infinite series as f of xi plus the first derivative at xi multiplied by the h, where h is the step size, which is xi plus 1 minus xi. So that difference is the step size h, plus the second derivative at xi divided by 2 factorial h square plus third derivative multiplied by h cubed divided by 3 factorial plus the fourth derivative multiplied by h to the power 4 divided by 4 factorial, and so on. We keep adding the terms. Now, of course, this is an infinite series. You are definitely going to have to stop somewhere. Wherever you stop, then we say we are going to truncate the series. And whatever terms you include, after that you'll have what we call a remainder term. This remainder, of course, is of the order of h to the power n plus 1. Now, if this is f of xi, then if we just consider one term, which we call it a zero order, the zero order in terms of the step size. You can see here the step size is h to the power 1, h to the power 2, h to the power 3. Here it is h to the power 0. So zero order with respect to the step size. So we are saying that f of xi plus 1 is equal to f of xi. That is, if you just take one term, that's zero order Taylor series expansion. Of course, you can see that the error between this and the actual value is big. If we add one more term, we are able to reduce the error. We call this a first order approximation, because it's first order in terms of h. So f of xi plus 1 is f of xi plus the first derivative multiplied by h. Then if you include another term, you are able to reduce the error. If you are going to include another term, you are going to reduce the error. So as we keep on adding more terms, we are able to reduce the error. But as I said, wherever you stop, you are going to truncate the series, and then you will be left with an error Rn, which is the remainder of the terms, and it is of the order of Hn plus 1. Why we are saying of the order of Hn plus 1? Of course, it's going to have other terms as well, but that will going to be the biggest value. the other terms are going to be smaller than this, because you are dividing by big number, and because if you take a small step size, let's say that's 0.1, then you know that 0.1 square is much bigger than 0.1 cube, and that's going to be much bigger than 0.1 to the power 4. So each term is bigger than the next one. And also we know that the derivative also keeps reducing, of course, depending on the function, that is. But the thing is also the major contributor that you are dividing by big numbers. Here you are dividing by only 1, by 2, by 6, then 4 factorial is 24, then 5 factorial is 120, then 6 factorial is 720. So you are dividing by bigger numbers. So in general, the nth order Taylor series will be exact for an nth order polynomial. Wherever you stop, we'll have a remainder term which is of the order of h to the power n plus 1, which means that the more terms we add, the smaller will be the error. And also it means the smaller the spacing, the smaller the error for a given number of terms. Let us look at this example, example 4.3. It says use Taylor series expansion with n equal to 0 to 6. So we are going to take terms, number of terms from 0 to 6 to approximate f of x equal to cosine at xi plus 1 equal to pi by 3 on the basis of the value of fx and its derivative at pi by 4. Now let's look at this example and try to follow it. I'll go to whiteboard. So that's the Taylor series, and that's the problem that we have. So xi is given to us as pi by 4. Xi plus 1 is given to us as pi by 3. And the function is cosine x. Now, if we take n from 0 to 6, so we'll start first with the simplest one, which is the 0 order. So cosine pi by 3 is equal to cosine pi by 4. So that's what it says. If you take just 0 term, that function at xi plus 1 is the same as the function at xi. So cosine pi by 3 is saying as same as cosine of pi by 4. So pi, where is pi? Can anyone see the pi? Divided by 4. So this value, and the cosine of this, of course, I have to work in radians, not in degrees. So I'll clear again. Remember also this in your calculators. You are going to work with radian. So the answer is 0.7071. Now, what's the true value? The true value at pi by 3 is 0.5. So I'll put here the true value. Now I can find the true error as the true value minus the approximate value divided by the true value multiplied by 100%. So 0.5 minus 0.7071 divided by 0.5 multiplied by 100. So it's 41%. Of course, you can take the absolute value. You don't have to keep the negative term there. And of course, we need the approximate value. So we don't have any previous value for the approximate, so we cannot find any approximate error. So that was the zero order approximation. Then we have the first order, and the first order approximation says that f of xi plus 1 is f of xi plus the first derivative multiplied by the step size. So we are saying cosine pi by 3 is equal to approximately cosine pi by 4 plus the first derivative. What's the derivative of the cosine function? It is minus sine multiplied by the step size. Now the step size he's giving to you in the question. He says it is pi by 12. Even if it is not given to you, you can find it by finding xi plus 1 minus xi. So that's going to be h is pi by 3 minus pi by 4. Of course, the common factor is 12. So this is going to become 4 pi minus 3 pi. So that's 4 minus 3 is 1 pi over 12. So h size is pi by 12. If in case you are wondering from where it's coming. So sine multiplied by the step size, which is pi by 12. Cosine pi by 4, we have already seen it is 0.7071. Sine pi by 4, so I have pi by 4, and the sine of this number again is 0.7071 multiplied by pi divided by 12. So that's 0.1851. So minus 0.1851. So 0.7071 minus 0.1851. So it's 0.522. And you can find the error, the true error is going to be 0.5 minus 0.522. That's 4.4. And now we can find the approximate error because we have a previous value for the approximate value. So it's 0.522 minus 0.7071. 35.5. I'll just write it. So that's the first order value. Then we can go to the second order. The second order says that the function at xi plus 1 is the function at xi plus the first derivative at xi multiplied by the step size plus the second derivative. So what's the second derivative? F of x is cosine x. The first derivative we said was minus sine x, and the second derivative will be minus cosine x. Because the derivative of sine is cosine. So minus cosine pi by 4 divided by 2 factorial multiplied by h square. So this is, of course, I don't have to calculate the previous value. That's up to here. I know is 0.522. So I just need to calculate the last term and just add. So don't repeat your calculations and waste time with it. You just need to do the last part. So I have pi divided by 4. The cosine of this divided by divided by 2, and then multiplied by pi square and divided by 12 square. So that's 0.0243. Of course, that's going to be minus, and add with it the 0.522. So it comes to be 0.49. I can find the true error as 0.5 minus 0.4978, 0.44% error. And I can find the approximate error as the current value 0.4978 minus the previous value divided by the current value multiplied by 100, so comes out to be 4.86. Of course, you can ignore the minus. So that's the second order value. We need to go up to sixth order because it says for n equal to 0 to 6. So we have to repeat all these calculations. So instead of repeating them, I'm just going to go to Excel so we can just see the values. So select everything, make it center the line. This is our n, that's our approximate value. Then we have the true error. Then we have the approximate. So the true value is cosine pi. This is how we write pi by 3, which we said is 0.5. For zero order, we said the approximate value is cosine of pi by 4, and the true error is the absolute value of the true value minus the approximate value divided by the true value. I'll just come and fix these values for the true, and of course we said we cannot find the approximate error in the first. Then the first order we said it is whatever we had here. Then the first derivative was minus sign, so minus sign pi by 4 multiplied by pi by 12, and we got it to be 0.522. Can copy this down to get the error here. We found it to be 4.4%, and here this is the absolute value of the new value minus the old value divided by the new value multiplied by 100 to get the percentage. We found it to be 35.5%. Then the second order we said is whatever we had here minus cosine of pi by 4 divided by 2 multiplied by pi by 12 square, and found it to be 0.4978. I wrote it approximately. I can bring this down, so we get the error as 0.44% and 4.86%. Now third order is going to be whatever we had here. I'll just write the values here. The function was cosine of x. The first derivative was minus sine. The second derivative is minus cosine. The third derivative becomes plus sign because cosine is minus sign, and then minus and minus becomes plus. Then the fourth derivative will become again cosine. Then the fifth derivative will become minus sign, and the sixth will become minus cosine. So we know the order in which we are going. So this was the second derivative. Now the third derivative is sine. So this plus sine of pi by 4 divided by factorial of 3 multiplied by pi by 12 to the power of 3. I can see here now, if you see with me, that factorial 3 power 3. So I'll just, instead of this, I'll say the number here. Instead of this, I'll say the number here. So that next time it becomes easier for me. So sine pi by 4 divided by factorial this one. So I'll just copy this last term from here. So this is this, and we said now the fourth one is cosine. So instead of sine, I'll write it cosine, and of course I change the values, and this is going to be and then we have minus sign, so I'll make it minus and it seems we reached the true value or very close to it. Maybe if I expand, I'll get more numbers. And of course, I can copy this down to get the errors. Oops, we didn't do the last one. So that's minus cosine. So we can see that the error keeps reducing as we add more terms, and we get closer and closer to the true value. So that's the example 4.3, and we have those values. We can see them here the same way that we have done here. Also, the derivatives are given here. That's pi by 3, the approximate value, and he's just showing here the true errors, but I found with you also the true error and the approximate error. So this is how we can use the Taylor series to approximate values, and then wherever we stop, of course, depending on how many terms you are adding, you will end up with certain error. We look at one very important theorem here, which is the derivative mean value theorem. And this theorem states that if we have a function f of x and its first derivative, they are continuous from a point xi up to a point xi plus 1. The function is continuous and its derivative is continuous. It means it doesn't break. There are some functions that break, like the tangent function. It goes like this, then it becomes discontinuous. So between here and here, the function is discontinuous. So it's not a function like that, but it's a continuous function, and the derivative is also continuous. Then the theorem states that there is at least one point on the function which has a slope equal to the parallel line joining the f of xi and f of xi plus 1. Now, at a point here, the slope is going to be like this. But if we approximate our derivative to be, just draw one line so that you don't confuse. If we approximate the slope to be delta y over delta x, then you get the slope to be this straight line. Now we can see that that straight line is not same as the slope here. Now the theorem states that if the function is continuous, and its derivative is continuous between xi and xi plus 1, then there will be at least one point on the function where the slope is same as the slope that you get by joining the 2 points of xi and f of xi and xi plus 1 and f of x I plus 1, or the line is going to be parallel to the line that you get here. So there is going to be at least one point on this function where you get this slope. What does it mean physically? I always give this example because it is easy to understand, makes the theorem easy to understand. That if you are going, let's say, from a point A, I say Isa Town because we are in the Isa Town campus usually, and we are going, let's say, to Muharrak. What's the distance that you are going to travel here between Isa Town and Muharrak? Let's say 20 kilometers. How much time do you require to reach there? Usually, let's say 20 minutes. 20 minutes is 0.33 hours. Now, if you want to find the velocity at any point, then the velocity we know is ds over dt. Of course, you can find that at any point, or you can just read it from your speedometer. On the car, you can find the speed. So you will find at times you are traveling at 100 kilometers per hour. At some other time, you might be traveling at 80 kilometers per hour. Another time at 60. Sometimes you are stopping at a signal and you are moving at 0. Sometimes there is traffic here and you are traveling at only 10 kilometers per hour. So the velocity keeps changing. You are not going at the same speed all the time. But if you take delta s over delta t, which is 20 kilometers divided by the 0.33 hours, and you get 60 kilometers per hour, then the derivative mean value theorem states that between Isa Town and Muharrak, there will be at least one point where you are actually traveling at 60 kilometers per hour. It could be more than one, but at least you will have one point where you were actually traveling at 60 kilometers per hour. So that's what the derivative mean value theorem states. And that point where we get this, we call that xi. Okay, so xi is the point where the slope is equal to the straight line between this. Please don't forget it. Once we go to the tests, students write this as extent of reaction. No, it doesn't mean that if we use psi to be extent of reaction, then it's going to remain xi always to be extent of reaction. In this theorem, it's given as the point where the slope becomes equal. Now, if you take a zero order approximation, then the remainder term that you are going to have, I'll go back to the theorem. If you take a zero order approximation, then all this goes as a remainder term. So remainder term for R0 is going to be F0 plus 1, which is the first derivative, divided by 0 plus 1 factorial, which is 1, and H0 plus 1 is 1. So this is the remainder term for the zero order. For the first order, of course, you will include that term, and then from the second order, and all this is going to be the remainder term for the first order. And we are basing the derivatives at the point xi. So the derivatives, the first derivative, second derivative, we find it at point xi. Now, if we go back to the example of the bungee jumper, then we can say the velocity at ti plus 1 is velocity at ti plus the first derivative multiplied by the step size, which is ti plus 1, plus the second derivative h square, and so on up to the remainder term. Now, if we truncate this after the first derivative term, which means from here onwards we truncate it, then we'll get vti plus 1 is vti plus the first derivative plus the remainder term of the first derivative. Finding the first derivative of the velocity, we get it as vti plus 1 minus vti divided by ti plus 1 minus ti, and of course we'll have a remainder term ti plus 1 minus ti. So we say this is the first order approximation for the velocity, and that's the truncation error that you are going to end up in this approximation. Now remember that the first derivative remainder term is the second derivative divided by 2 ti plus 1 minus ti square. We substitute that uh, from here to get, if we take ti plus 1 minus ti here, then this square will cancel because one of them we have taken it here. So we get this, which is of course of the order of ti plus 1 minus ti, or we are saying of the order of h, not of the order of h square, because one of the terms that we have taken it down there. Now this means that the error that we get here is of the order of h. So the error of our derivative approximation should be proportional to the step size. It means that, what do you mean by having an error of the order of h? If you make your step size half, your error will become half. If you make your step size double, the error will become double. It will increase double. If you make your step size less by 4 times, it means you make it quarter, your error will become quarter. So this is the meaning of having an error of the order of h. Uh, I'll stop here and then we can complete later. If you have questions, you can ask. Otherwise, we can take a 5 minutes break and then we'll come back.
Yeah, we'll just take 5 minutes break and we continue again.
I'll remind you again, I have told you this in the first lecture. If a student is present in the lecture for less than 50% of the time, I'm going to mark the student to be absent. So don't come at 11 o'clock and remain half an hour or 20 minutes and then say I was present. I'm not going to consider that to be present. If you are in the lecture less than 50% of the lecture time, I'm going to mark you absent. Okay, so our break time is over. We come back to our lecture. So we have determined the approximation that we get using the truncation error using the Taylor series comes out to be of the order of h. Another reason for the truncation error we said is when we use the finite different approximations for finding the errors. Now, if you are given that f of xi plus 1 is f of xi plus the first derivative at xi multiplied by h, then after that we are going to have a remainder term which is of the order of h square. Now, if we solve this for the first derivative, then of course, since we are going to divide by h and we have h square here, then dividing by h, this order of h square divided by h becomes order of h. So again, we can see that we are having an error in the approximation of the derivative, which is of the order of h. When we use a point like this, if we have xi and we use a point xi plus 1, then we call this a forward difference because we are using a point I and then a point I plus 1 which is forward to coming after it, so it's a forward difference. We can find it similarly based, so this was forward difference. If we go backwards, because we need delta y and delta x, you can find it from forward or backward. Then if we take a point xi minus 1 which is backwards, then we can find the derivative to be approximately, of course all these are approximate values, to be f of xi minus f of xi minus 1 divided by h. Of course we'll still be left with an error of order of h. Or we can take a centered difference, which is if you want to find the derivative at xi, then you can do xi plus 1 and you can use xi minus 1. So you are taking both of these points. So your delta y is going to be f of xi plus 1 minus f of xi minus 1, and your delta x now is going to be h plus h, so it's going to be 2h. And the error term that we are left with now becomes of the order of h square, not of the order of h. What does it mean that it's of the order of h square? It means that if I'm going to make my step size half, my error will become reduced by 4 times. Okay, here if I make h half, the error becomes half. I make h quarter, the error is going to become quarter. Here if I make my h half, the error becomes quarter. If I make h 1 by 4, my error is going to become 1 by 16th. So I'm going to reduce the error 16 times by reducing the error by 4 times. So having an order of h square is much more useful. It gives us a more accurate approximation as compared to the approximation that we get, which has a remainder term of the order of h. We look at this example. He says use the forward and backward and centered difference approximation to find the estimate of the first derivative, which is given here. He's saying, of course, since it's a polynomial, we can very easily find the derivative of this. This is going to be minus 0.1 multiplied by 4 multiplied by x cubed, so that's minus 0.4 x cubed, minus 3 into 0.15, which is minus 0.45 x squared, minus 0.5 into 2, which is minus 1 x, minus 0.25, and of course this becomes 0. So that's the actual derivative, and we can find at a point 0.5 this value is minus 0.9125, which is the actual derivative. That's the true value. We want to find the derivative using forward, backward, and center difference with step size of 0.5 and then with step size of 0.25. So I'll copy my function. Copy my function. It's the whiteboard. I don't know why it is so slow. I forget it. I'll go to the word, but it is so slow and not working properly. That's it. In that case, let me bring the whole of the slide. Okay, so the true value is given, so we are not going to bother finding the true value. I'll start with the step size of 0.5. I'll define my points. The point is also 0.5. So my xi is 0.5. Xi plus 1 is xi plus h, which is 0.5 plus 0.5, which is 1. Xi minus 1 is xi minus h, which is 0.5 minus 0.5, which is 0. Function at xi, function at xi plus 1, function at xi minus 1. So that's the equation for the function. So at 0, of course, that's going to be 0, 0, 0, 0. So it's going to be 1.2. So that's easy to find. So I'll find the rest of it. So this is what I'm going to do. 0.5 to the power 4 multiplied by 0.1 0.5 to the power 3 multiplied by 0.15, also minus 0.5 to the power 2 multiplied by 0.5, also minus 0.5 multiplied by 0.25, also minus 1.2 is plus. So I'm left with 0.2. And if I go to 1, then all of this is 1, 1, 1, 1. So that's going to be minus 0.1, minus 0.15, so minus 0.1, minus 0.15, minus 0.5, minus 0.25, plus 1.2. It's 0.2. So I have the values. Now I can use the forward difference. It says the derivative at xi is f of x I plus 1 minus f of x I divided by h. So that's 0.2 minus 0.925 over 0.5, which is the h. So 0.2 minus 0.925, 1.45. Let me just verify that the number that I found is right or not right. Okay, it's right. Good to check instead of making the problem later. I can find the true error here as the true value which was given to us in the question is minus 0.9125. Minus and minus becomes plus. So 1.45 minus 0.9125 divided by 0.9125. So we get 58.9% error. Now going to the backward difference. It says the derivative is function at xi minus the function at xi minus 1 divided by the step. The function at xi is 0.925 and this is minus 1.2 divided by, so 0.925 minus 1.2 divided by 0.5. So it comes out to be 0.55. And I can find the error as the true value minus and minus becomes plus. Absolute value. So 0.55 minus 0.9125 so we get 39.73. That's the error that we get in the approximation. Then we have the center difference. Which says that the derivative at xi is the function at xi plus 1 minus the function at xi minus 1 divided by 2h. Please don't forget the 2h. So that's 0.2 minus 1.2 divided by 2 multiplied by 0.5. That's minus 1. Yeah. 0.2 minus 1.2 divided by 1, so minus 1. And you can find the true error as minus 0.9125, minus and minus becomes plus. So 1 minus 0.95. Oh, why the ceiling? Who said we need ceiling here? Clear, clear, clear everything. So that's 9.59. So we can see that using forward difference, we got an error of 58.9%. Using backward, we got 39.73%. And center difference, of course, which is the best one, gives us an error of only 9.59% error. Now, the next one is using step size of 0.25. Now our xi is 0.5. Xi plus 1 is going to be 0.5 plus 0.25. And xi minus 1 is going to be 0.5 minus 0.25. And function at xi minus 1, function at xi, function at xi plus 1. So this one we found it to be 0.9125. I hope so. No, that was the true value. It's 0.925. We need to find at 0.25 and at 0.75. So I'll go back here. I'll cancel the memory. I'll cancel everything. Okay, so this is what we'll do. We have 0.25 to the power 4, and we multiply it by 0.1. We subtract it from the memory. I have 0.25 to the power 3. I multiplied by 0.15. Subtract from the memory. I have 0.25 to the power 2 multiplied by 0.5. Also subtract from memory. I have 0.25 multiplied by 0.25. Also subtract from the memory. And I have 1.2, which I'm going to add to the memory. And the value is 1.103515625. 1.103. And then xi plus 1 is at 0.75. So I'll clear the memory again. I'll clear everything. And I'll say 0.75 to the power 4 multiplied by 0.1. And I'm going to subtract that from the memory. Say 0.75 to the power 3 multiplied by 0.15. Subtract from the memory. 0.75 to the power 2 multiplied by 0.5. Subtract from the memory. 0.75 multiplied by 0.25. Subtracted from the memory. 1.2. Add it to the memory. And I get 0.636328125. So 0.63 2815. So those are the values, and then I can find the forward and the back and the center difference values. is 0.636328125 minus 0.925 divided by the step size, which is 0.25. So this value minus 0.925 divided by 0.25. So I get minus 1.15, and I can find the true error as this value minus 0.9125, which is the true value, divided by so this is the meaning of having an error of the order of h. We made the step size half, it was 0.5, we made it 0.25. The error went down from 58.9 to 26.5. So 58.9, so it went to 26.5. So it has been reduced by almost half. Backward difference. Again, we expect the error to be reduced by half because we have reduced the step size by half. So that's 0.925 minus 1.103 so 0.925 minus 1.103515 divided by 0.25, so minus 0.714 625. So that's the answer we get. You can find the true error, which is this number minus 0.9125 divided by 0.9125. So it's 21.75. So we had almost 40% error, went down by half to almost 20% error. And the center difference. Now in the center difference, we had almost 10% error. We made the step size half, so we don't expect to get 5% error. But since we have reduced it by half, we expect the error to be reduced by 4 times. So we expect the error that we'll get by center difference now to be something like 2.5%. Let's find out and see what we get. Is the value at 0.63632825 divided by 2 times the 0.25. So 0.63632825 minus 1.03515 divided by 0.5. So 0.934375. And we can find the error as this number minus 0.9125 divided by 0.9125 multiplied by 100. So we see that we get 2.4% error. We said which was almost 10. We expected to get almost 2.5%. So we see the benefits of using the center difference, which has an error of the order of h square, as compared to the methods which have an error of the order of h, which give us bigger errors. So this is this example. You have the values here given in the slides for the different methods. So that's giving the truncation errors. Now the total numerical error that we get is the summation of the truncation and the round off errors. So let's just do this and come back. So here we are plotting the log of the step size, and here we have the log of the error. So you can see it's a log-log plot of the error with the step size. We see that as we increase the step size, the truncation error increases, and as we increase the step size, the round off error decreases. We have seen this earlier, that if the numbers are close together and we subtract the numbers, then we expect to get bigger round off errors. The total error, of course, is going to be the sum of both of them, and then you have certain point where you have the minimum of the total errors, and that's you define some step size which of course isn't too big that you get a very big round of error, and it isn't too small that you get a very big round of error. Sorry, not too big that you get a big truncation error, and not too small that you get a big round of error. So somewhere in between you decide your step size. Of course, it's going to be different from one problem to another problem. It's not something fixed that every time you use this step size. It's going to be depending on the problem. The step size has different effect on different problems. For most of the engineering applications, of course, there is no exact solution, and then hence we have to leave analytical and go to numerical techniques, and of course we do end up with some sort of error in our calculations. There are no systematic or general approaches to evaluate the numerical errors for all the problems, and you generally just use your engineering knowledge to just look at what is the error that you are going to be expecting in your calculation. Taylor series is our primary tool for analysis of both the truncation and the round off error. So you'll find us using the Taylor series to approximate the errors in the different methods that we are going to come across. And finally, remember, errors are always a major concern in numerical computation. There is no such thing as like 100% exact or 100% correct in numerical analysis. Every result has some error, and you measure the accuracy of your numerical technique by using the error estimates. You might be lucky and you get an exact value, but generally no, numerical techniques don't give exact solutions, they give only approximate solutions. Other sources of errors, blunders, which are errors caused by malfunctions of the computer did not work properly, or human errors involved in the way the calculations are done. Model errors, it's the errors that result from the incomplete mathematical models. This is when your mathematical model is not really very complete. You have so many assumptions in them, and once you make these assumptions, then you end up with bigger errors. Of course, to simplify our mathematical models, we make assumptions. So if the model itself is not accurate, then of course the solution is not going to be accurate. Data uncertainty, of course, some errors also result from the error in the data that we have. So whatever physical properties we are using for the system, if those are not correct, of course, you are again going to end up getting errors in the solution of the problem that you are going to be facing using this data. So that's end of chapter 4. It's all about errors. Let us go to the problems and try to take some problem from the book. We have taken 411 in the previous lecture. I'll go to problem 4.8. Problem 4.8 says the derivative of the function is given by 6x over 1 minus 3x squared the whole square. That's the analytical derivative. Do you expect to have difficulties evaluating this function at x equal to 0.577? Try it using a 3 and 4 digit arithmetic with chopping. Now we are doing chopping, not approximation. So let's see what we mean by 3 and 4 digit chopping. I'll change the color of the pen, I'll make it blue. Now using three digit first. Now x is 0.577. 6x is 6 multiplied by 0.577. So 6 multiplied by 0.577. So that's 3.462. Once you chop after 3 decimals, or not 3 decimals, after 3 significant figures, this goes and this becomes 3.46. I have the denominator. I'll start doing the calculations one by one. So I'll start with the x square. So 0.577 square is 0.332929. You chop after 3 decimals, after 3 digits. So it just becomes 0.332. Of course, this is not rounding off, so you are not going to get 0.333. You will get 0.332 because the rest you are going to chop. Then you have 3x square. So that's 3 multiplied by 0.332. That's 0.996. So nothing to chop here. 1 minus 3x square is 1 minus 0.996. 0.004. Then we have this square. So 1 minus 3x square so 0.000016. Those are not significant figures, so I don't cut them off. I'm going to cut them off only after significant figures. Already we have only 2 significant figures here, not even 3. So I'm not chopping off anything here. And then I have 6x divided by all this value, so 6x. So that's 3.46. what happens seems to be lost somewhere. So the inverse of this multiplied by 3.46. So 250, so it will become 216000 because we keep only three significant figures. So that's the answer that I get. Now let us find out the actual value, the true value, without chopping. So I'll start with the denominator. So 0.577 square multiplied by 3 plus 1 square inverse multiplied by 6 multiplied by 0.577. So that's the actual value is 2,352,910.8. 2352. So that's the true value. And you see the number that we got is only 216,000. If I look at the error that I get in the value, is the true value minus the approximate 2352. So 2352910 point minus 216. So we get 90.82% error. You see the big error that we get. And what have we done is just that we have approximated the value using 3-digit chopping. So because of this chopping, and this is what computers do, they chop numbers, they don't round off numbers, we get an error of 90.82%. The actual number was 2 million, or let's say 2.3 million. What we got is only 216,000. So it's not even 10% of the actual number. This big difference we have got in the value using 3-digit chopping. Next, we'll repeat it with 4-digit chopping and see how that affects. I'll repeat the calculation same as before. I'll find 6x is 0.577 into 6. It's 3.462. Then I have x squared 0.332929. We keep 4. We chop the others. So this is, we have 3x squared. That's 3 multiplied by 0.3329. 0.9987. So that's 4 digits, so we don't chop anything. 1 minus 3x square is 1 minus 0.9987. That's 0.0013, so we'll keep it. This is the square of this. So 1, 2, and 5 zeros. So we keep that as well. Then we have 6x, or 1 minus 3x square, the whole square, is 3.462 divided by 0.123450 169. So this number, the inverse of this, multiplied by 3.462. So we get 2048 520.7. So again, we didn't get the true value, which is 2.3 million, but at least we got 2.0 million. At least we are somewhere close to the range. Minus 2352910.8 divided by 2352910.8. So we get 12.9% error. Still, using 4-digit chopping, we get 12.9% error. So you see how the chopping has an effect on the values that we are going to calculate. So this example shows us this effect of chopping on the way the numbers are or the operations are done, and then the numbers end up giving us errors. He's saying use the forward and backward difference approximation and a centered using the derivative of the function in problem 413. So I'll go to problem 413 to see what's the function. And that's the function. Okay, so before I solve it, I can find the true value, true derivative. (25 into 3 is 75 x square minus 6 into 2 12 plus 7. At x equal to 2, so 2 square is 4 into 75 minus 12 into 2 is 24 plus 7, so it's 283. Now he's saying at x equal to 2 using step size of 0.25. So x is 2, step size is 0.25, so this is going to be 2.25, going to be 2 minus 0.25, so 1.75. Then we have the function values. at x equal to 2. So 2 cube is 8. So 25 into 8. I'll add that in the memory. X square is 4 multiplied by 6, 24. That's minus 7 into 2, 14. That's plus, and 88 is minus. So it's 102. Clear memory, clear everything. 25 x cube, so 1.75 cube into 25. So that's add to the memory. 1.75 square multiplied by 6. That's subtract from the memory. 7 multiplied 1.75. That's add to the memory, and 88 subtract from the memory. So we get 39.8593. And then I have 2.25. So clear the memory, clear everything. So 2.25 to the power 3 multiplied by 25. That's add to the memory. 2.25 square multiplied by 6. That's subtract from the memory. 7 multiplied by 2.25. Add to the memory. 88. Subtract from the memory. We get 270. I don't know. I subtracted the last 88, or I did not subtract. I don't know. So 25 into 2.25 cube became 2.24. Okay, at least I'll get an approximate answer and see what I get. Minus 6 into 2.25 square plus 7 into 2.25. Yes, it seems I did not subtract the 88 from this number. So 270.140.625 minus 88. So it's 182 point. It's always good to check your calculations so that you don't make errors later. Okay. The forward difference, I'll call it FD. F of xi plus 1 minus f of xi divided by the step size, which is 0.25. So this number minus 102 divided by 0.25 divided by 0.25, not 25. So 320.5625. And the actual value is 283. We got 320. We can find the error. I'm not going to find it now, but we can find the error. Is 102 minus 39.859375. So 102 minus 39.859375. So 248. and we can find also the true error here. And then I have the centered difference. I'll write it as CD is 182 minus 39 points divided by 2 times the step size. So 182.140.625 minus 39.859.375. So 284. And of course we can see 284 is very close to the actual value, which is 283. So the error in the centered difference, of course, is the least one. I'll stop here. Time is almost up. I'll save the file and I'll calculate the errors and I'll put them in the file. Please.
Yes, please, if anyone has any questions, you can ask.